Uh, Hello everyone. My name is Hieu. Today I will present my finite element methods final project. The topic is stress analysis of cylindrical robot arm. Uh, Here is the outline of my presentation. First, the introduction, motivation, and methods. Second, the finite element methods model. Third, the math and thus and three element tiles. Fourth, the conversion study. Fifth, the numerical results. And finally, the conclusion and future works. Um, let's start with the introduction. Um, a robot arms carry a load at its three ends. This creates a large bending moment at the joint between the arm and the column. So we must check the stress and deformation before we build it. Um, Finite element methods have predicted this quickly. This is a classic problem. Uh, cantilevers beams under a tip load. The accuracy depends on two things, the element order and the mesh density. One important point, the shock causes the joint causes a stress singularity. This is a key theme of my study. The next one is FEM module geometry. Now, this module geometry has four parts. The base is a circular foundation, and it is fully fixed. The column is a vertical cylinder support. The arm is a horizontal cantilever beam, and the end block is where we apply the load. I do a static structural analysis with linear isotropic and small deformation assumptions. After chemistry, the last step is the material and the boundary conditions. For the for the materials I use a structural steel, the ANSYS default. Uh, and the adjunct modulus is two 200 GPa, and the Poisson ratio is 0.3. For the boundary conditions, the bottom face of the base is fully fixed, and I apply a force of 100 Newton in the minus z direction at the end block. Um, to make a fair comparison, I use the same geometry and the same 5 millimeter base size. Only the element type change. The first is TET4, a linear tetrahedron for lot corner only. Is in no order. The second is TET10, a quadratic tetrahedron with mid-side note. It captures stress gradient well. The third is E20, a quadratic hexahedron, a brick element. Its efficiency per degree of freedom. So the next one is conversion study. Here is here the conversion study. I do the TET10 element and refine the mesh from 10 down to 2 millimeter. The deformations stay almost the same, about 0.1187 millimeters. The change is less than 0.2% per step. So the deformation converges, but the stress is different. It keeps rising as the mesh gets finer, up to 4.4 MPa. The stress doesn't converge. The reason is the stress peak at the shaft arm column corners. This is the stress singularity. So the next one is the numerical results. Now I compare all three element types. Same 5 millimeter mass, same 100 Newton force, and same fixed base. TET4 give the lowest values. Its stress is 21% below TET10, and TET10 is my reference, as EH20 gives almost the same deformation as TET10, about 0.1187 millimeters, but its stress is 20% higher. The critical location is on the arm column joint. So let's me look closer. First, TET against TET10. So setup on a TET4 the linear element. The deformation is 0.0992 and the stress is 2.075. It is too stiff. This is a shear knocking. Is underestimated and also sorry I is under underestimated both by about 20%. It's in it is reliable. Step 2 is TET10. Also, it's my reference. The deformation is 0.1184 and the stress is 2.638. The missile notes capture the stress gradient well. This gives the best balance of accuracy and cost. Let's let's check the SEH20 result to confirm our finding. So if the information is 0.1186 millimeter, also the same as TET10. This is important to different element types give the same answer. It confirm the displacement convergence. So this stress is 3.164 MPa, about 20% higher. But this is only because the 424,000 element result the corners peak more sharply. Uh, it's not an error, it is a singularity again. So let me discuss the result distribution. The deformation peak is always at the free end and the arm. This is classic cantilever behavior. The chest peak is always the arm column joint because of because of the largest bending moment and the sharp corner. And one more thing, on three element type only type gives the same distribution pattern. Only the peak magnitudes are different because of the element order and the mass density. So let me summarize everything in the conclusion. I analyze three element types. So the requirements in math. TET4 is too steep and underestimated by about 20%. TET10 and SEAK20 give a canvas deformation of about 0.1187 millimeter. The deformation can be just, but this stretch does not because of the corner's singularity. The critical location is the arm column joint from future work. I can ask a few nets of the joint to guess a canvas chest, evaluate the chest in the arm body for a safety factor, a 10 to 40 or motor analysis and compare with the analytical solution to verify the model. So thank you for listening.